Alright, so hi everyone. Today we are going to tackle the last topic for our second chapter in Mathematics in the Modern World, and we'll have to talk about logic and formality. So what comes first in your mind when we speak about logic? Could we say that if a person thinks correctly, then he has a logic? Perhaps until now there are some people arguing whether a logic is an art or it is a science. Now, whether it is an art or a science, studying logic could be very important not only in the field of mathematics, but also in other sciences such as natural science and social science. Alright, so in this discussion, we will studying the fundamental concept of logic, but basically logic as a mathematical language. So it means that this also under our topic mathematical language. Specifically, we're going to deal with the formal versus informal logic and the deductive versus inductive reasoning. And what are our objectives? So, your task to define what logic is, tell whether this statement is formal or non-formal, and show the relationship between grammar in English and logic in mathematics. Let's see. Hi. Right. So, say we have here our first word that we can define logic, the science of correct reasoning. So, in our social science courses, logic could define as the study of the principles of correct reasoning. It's study of or the science of correct reasoning, and it is not a psychology of reasoning, of course. Based on the definition, which is logic is the study of the principle of correct reasoning. One of the principles in logic that is very much important to study is on how to determine the validity of one's argument. So studying mathematics is also studying theorems. And the proof of the theorem uses the principle of arguments in logic. So in this case, we could say that the language of mathematics is the logic. Next, we have reasoning. So, reasoning is the drawing of inferences or conclusions from unknown or assumed facts. So, it's very evident that reasoning is one of the most used thing when we are solving a problem. So, when solving a problem, one must understand the question. So we gather all the pertinent facts, analyze the problem, compare with previous problems. We perhaps use pictures or formulas or patterns to solve the problem. And that's how you go, or that's what the process goes on when we are drawing an inference to a certain assumed facts. And now we have mathematical logic. When we say mathematical logic, it is a statement about mathematical objects that are taken seriously as mathematical objects on their own right. So we can formulate a precise mathematical way in its definition, theorem, lemma, conjecture, corollary, propositions, and the methods of proof, which will be discussed in our next lesson. So it means that those types of mathematical logics that we will define later on are definition, theorem, lemma, conjecture, corollary, and propositions. So let's see on that. First, we need to understand what is formality. As stated by Halin, F. and Dewell, J.M. in the Formality of Language Definition in Measurement book, It is an expression that is completely formal when when its context is independent and precise. So it represents a clear distinction which is invariant under changes of context. In mathematics, we are always dealing in a formal way. So that's how go formality. Now let's talk about the first type of mathematical logic, the definition. One of the major parts of formality in mathematics is the definition itself. So when we say definition, it is a formal statement of the meaning of a word or group of words, and it could stand alone. So let's see the example that we have. First, I would like you to define what is right triangle. So, what is the exact or formal definition of this? So, a right triangle consists of two legs and a hypotenuse. The two legs meet at a 90-degree angle, and the hypotenuse is the longest side of the right triangle and is the side opposite to right angle. Here you will see the exactness or the preciseness, the precision of the definition of a right triangle. So that's how, or that's what we say one of the formal formal definition. Okay, that's how formality works in mathematics. And now let's try to define the second term, Carabao. Can you give a definition for this? Well, of course, everyone can give, depending on how they perceive a Carabao. Maybe some of you will define a Carabao as a black and strong animal that helps the farmer in plowing the rice field. But have you noticed that it is not a formal definition? Miss, how do you say so that this is not a formal definition? How about the cow and the horse? These are also an animal that could also help the farmers in plowing the field aside from the carabao. And how about the machine tractor? Are we not considering this machine that could possibly help our farmers in plowing the rice field? So, we cannot say that it is a formal definition since it cannot stand alone. And the definition that has a black and strong animal that helps the farmer in plowing the rice field, it can also be given to the other thing like cow or horse or even in machine tractor, because those things can help the farmer to plow the rice field. So I hope you understand the difference between formal definition and informal definition. When we say formal, the definition can stand alone and it's really precise. And when we talk about informal definition, it means it cannot stand alone. It's very wide, like that. So another statement that could we consider as a formal statement is the theorem. So you will encounter this word in all books of mathematics, especially if it is pure mathematics. So in your algebra subject during your high school days, have you studied different laws and principles in mathematics? Well, I bet yes. These are just really theorems that proven true and justified using the concept of mathematical logic, and all you need to do is to apply those laws and principles, and that's how you go, those theorems. Let's see the definition of it. A theorem is a statement that can be demonstrated to be true by accepted mathematical operations and arguments. So it means in general, a theorem is an embodiment of some general principle that makes it part of a larger theory. The process of showing a theorem to be correct is called a proof. So there should be an ongoing process or ongoing process of proving before we can say that one statement is a theorem. And I want to show to you the best example for the theorem that I know we all know this, the Pythagorean theorem or Pythagorean theorem. It depends on how you pronounce it. And this is very well-known theorem in mathematics. That's correct. The theorem stated that the square of the hypotenuse of a right triangle is equal to the sum of the squares of the other two sides. So if the hypotenuse, the side opposite to right angle, or what we call the long side, is called C, and the other two sides are A and B, then this theorem will have the formula a squared plus b squared is equals to c squared. So you will notice that the theorem is precise in a form of if-then statement. The if-then statement is one of the statements in logic. So a statement could not be considered theorem unless it was proven through using mathematical logic. So there should be mathematical logic. There should be a proof or a process of proving before we can have we can come up to a theorem. And let's see the definition of the proof, the one that we are talking about a while ago, because we said that to be able to consider a theorem that is true, it should undergo the process of proving. But what do we mean by proof or mathematical proof? Proof is a rigorous mathematical argument which unequivocally demonstrates the truth of a given proposition. Now let's define proposition. When we say proposition, it is a declarative statement that it is true or false but not both. So remember that it's either of the two is true or false, but not both of those statements are true and of course false. And this statement is another major part of formality, since all types of proposition are precise and concise. And let's talk about the first type or different types of proposition. First, we have negation, and from the word itself, you negate it. And let's see the definition that we have. The logical operation that takes a statement and changes it to a statement whose true or false value is opposite that of the original statement. So when you are getting the negation of any original statement, you're just taking the opposite of that statement. Let's see the example here. Say we have an original statement, I'm not an engineer. And how can I negate it? The statement, I am an engineer. And let's see the other example. So we have the original statement as Roderick attends mathematics class, and the negation of this statement is Roderick will not attend mathematics class. Let me add another example. Say as simple as I have an original statement that today is Monday, and the negation of the statement that I have today is Monday will be today is not Monday. That's how easy the negation is. And let's take a look at the other one. First, I have an example here. First statement, we have John eats rice, and the second statement is Maria drinks soda. So then the conjunction of the original statements will be John eats rice and Maria drinks soda. So in this example, we are talking about what we call conjunction. And what will be the conjunction is, if two statements are combined by the word and, then the proposition is called conjunction. So it's easy to remember that when you're dealing with conjunction, those statements being combined by the word and. That's why we have an example here. John eats rice and Maria drinks soda. And let's see the other one. We have disjunction. We have conjunction, and then we have disjunction. Any two statements can be combined by the word or to form a new statement, which is called the disjunction of the original two statements. Let's see the first example that we have. First statement is life is beautiful. The other statement, life is challenging. So how will you get the disjunction of this? Life is beautiful or challenging. We're just using or to get the disjunction of the original statements. Unlike with the conjunction, we are using the word and to combine those statements. And now we have conditional, our fourth type of proposition. It is expressed by if-then statement. So when you take a look at the statement and it will be in a form of if-then statement, then we can say that that statement will be a conditional statement. And the first statement would be a premise, and the second statement is the conclusion. So let's see the example that we have. First statement, you are absent, and second statement, you have a makeup assignment to complete. So when we are going to make this as in a conditional statement, if you are absent, then you have a makeup assignment to complete. So the premise here is you are absent, and the conclusion that we have here is you have a makeup assignment to complete. Let us have another example. Say the premise is if x is positive, then its square is also positive. So if x is positive, then its square is also positive. We can show the proposition is true with the use of one of the methods of proving. Say, I have positive 2. And when I get the square of 2, I have positive 4. So, by proving, then we can say the formal statement, if x is positive, then its square is also positive. That's how it goes. And let's move forward to the fifth type of proposition. We have biconditional. It uses a connector for two statements, if and only if. So for conditional, we are using if then, and then in biconditional, we are using the connectors if and only if. Say example, statement 1, I will attend mass. And another statement is tomorrow is Sunday. So how does it look when we get to use the biconditional statement? I will attend mass if and only if tomorrow is Sunday. So as you can see, there is a connector that which is if and only if. We use this to make our statement as a biconditional. Now we're done with the different types of proposition, and let's see the other mathematical logic. We have here COLLARY. When we say corollary, okay, it's not COLLARY, it should be corollary. Yeah, this is a typographical error. This is not COLLARY, it should be corollary. Alright. So what is corollary? In mathematics, it is also a proposition that follows with little or no proof required from one already proven. Let's see the example. The angles opposite two congruent sides of a triangle are also congruent. A corollary to that statement is that an equilateral triangle is also equiangular. That's the example for corollary statement in mathematics. Now let's see this lemma. The lemma that is also called the helping theorem. A lemma is a short theorem used in proving a larger theorem. So we have the example. Consider an arbitrary integer. Say we have integer 37. Suppose that we divide this by 7. Then what will be the quotient and the remainder? So we will have 37 is equals to 7 times 5, 35 plus 2 is 37. So it means that our quotient will be 7 when we divide 37 by 5, and the remainder will be 2. And when we divide 37 by 7, then we can get the quotient of 5 with the remainder, which is 2. So finally, let us generalize. So let A and B be any positive integers, and suppose that we divided A by B, we will obtain a quotient Q and a remainder R. That's how lemma goes. And let's see this last mathematical logic, the conjuncture or conjecture. A proposition which is consistent with known data but has neither been verified nor shown to be false. It is synonymous or identical with hypothesis, also known as educated guess. We can only disprove the truthfulness of a conjecture when, after using a counterexample, we found at least one that says the statement is false. So when we get the counterexample and there is at least one that says that a statement is false, then that statement will be considered as false as well. Say we have an example here. Let us say we have 75 different balls in a bingo urn. It labeled as 1 up to 75. What will be our conjecture? We could say that all number in an urn is a counting number from 1 to 75. Now let's talk about the two basic categories of human reasoning. Those are the deductive and the inductive reasoning. Both deductive and inductive arguments occur frequently naturally. Both forms of reasoning can be equally compelling and persuasive, and neither form is preferred over the other. So first, we have deductive reasoning from general premises which are known as presumed to be known to be more specific certain conclusions. So always remember that deductive, it takes out from general to specific, or GS. DGS. I used to remember deductive as DGS, or deductive general to specific. And when we say inductive, it is ISG, inductive reasoning from specific cases to more general but uncertain conclusions. When we say inductive, I always remember it as ISG, or inductive from specific to general conclusions. Alright, so let's talk about the deductive reasoning, or what we call the process of deduction. First here is the induction. Deduction is commonly associated with formal logic, can be called as formal logic, and it involves reasoning from known premises or premises presumed to be true to a certain conclusion. And then the conclusions reached are certain, inevitable, inescapable. And let's see the difference of deduction to the induction. This is commonly known as informal logic or everyday argument. So I would like you to remember that induction is ISG, induction from specific to general. It always involves drawing uncertain inferences based on probabilistic reasoning. And the conclusions reached are probable, reasonable, plausible, and believable. And this is the example of the Venn diagram of a deductive argument. Of course, first we have this yellow circle, vegetarian animals. All tortoises fall in the circle of animals that are vegetarians. So say we have Bessie. Bessie is one of the tortoise, or Bessie falls into the circle of animals that are tortoise. Then what will be the conclusion? Thus, Bessie must be a vegetarian, because from our original statement, or the general statement, that all tortoises fall in the circle of animals that are vegetarians. And I have Bessie, who is a tortoise. Then to be specific, Bessie must be a vegetarian. That's how deductive argument goes with it. It came from the general conclusion to specific premises. And let's see. To further understand, deductive reasoning is commonly found in natural sciences or hard sciences, less so in everyday arguments, unlike the inductive reasoning. And occasionally, everyday arguments do involve deductive reasoning. So, example, we have 2 or more persons are required to drive in the diamond line. So, you don't have 2 or more persons, therefore, you may not drive in the diamond line. So, from the general conclusion that there should be 2 or more, or the minimum number of persons should be 2 only, that is required to drive in the diamond lane. So it means, to be specific, you may not drive in the diamond lane if you're only one, you're alone, or you're only one, you don't have any companion. And in inductive reasoning, it is found in a courtroom, the boardroom, the classroom, and throughout the media. Most but not all everyday arguments are based on induction. So as I mentioned, most of those everyday arguments are falling under the inductive reasoning, but not all. Say we have example, the reasonable person standard in civil law and the beyond a reasonable doubt standard in criminal law. That's one of our example. And help you understand, when we say deductive, it's DGS, deductive from general to specific. When we say inductive, IST, the inductive is from specific to general premises. And this will be the end of our discussion about logic and formality for mathematical language.